Hello everybody, my name is Alex Matveev and I'm developer of PAS StarProf software that is developed under the brand PAS Suite. In this seminar we will talk about several ASME B31 and B31 issues needed to know for pipe stress engineers. The first issue is in B31 code and it is related to the stresses due to sustained loads. Let's check this equation from the code and we have a look at it. We will see that it includes the axial stress from the pressure and it includes the bending stress from the bending moment. But it doesn't include the stress caused by axial force. The same issue with occasional loads. It doesn't include the axial load stresses. Now let's check this model. For example, we have very tall riser, very tall pipe with a great weight. In this model we will have very high axial force and the stress caused by this axial force will be very high, but ASME B31 code ignore this stress and doesn't take it into account. So let's check this model using the StarProf software. Here you can see the original code stress calculated by original code equation, and this stress is very low. But if we will use this option to add the axial and torsion stresses into the bending stress calculation, sustained stress calculation, it is SL with asterisk, you will see that the stresses are much greater than allowable values. How does this stress calculated? The SL with asterisk is calculated according to the equation similar to ASME B31 code, and it is include the axial force stress and torsion moment stress. And for this model the difference is significant. If we doesn't take into account the axial force, the stress will be very low, but if we will take into account the axial force, the stress will become greater than allowable. So in real system we will have the failure here, but according to the code it's okay and you will not see any problem. Another issue is the same reason, but it's related to the expansion range stress. In ASME B31 code, it takes into account only bending moment. It doesn't take into account the axial force, doesn't take into account the torsion moments, only bending moment. So if you will create the design like this, the pipe that is restrained between two anchors, the code stress will be 0. The stress will be 0 because the bending moment is 0 in this model. But the real stress range will be huge and it will be greater than allowable because of very high axial force. So in this case you need to include the axial force stress and torsion stress too. You need to check this option in StarProf and software will automatically include the stresses from axial force and torsion moment into the stress calculation. And sometimes even experienced piping designer can make a mistake. If you have very big model, you can miss the wrong design when some part of the piping is restrained between two anchors. Now let me show you how to check this in the software. I will create the simple model. I will use ASME B31 code. The ambient temperature will be 0. Now I create the pipe. For example, 3 meters. This is diameter, wall thickness, the material. The pressure will be 0. The temperature will be 150 degrees. And let's add the fluid date. Here is the pipe. Now I will add the anchors here. First anchor and second anchor. And now let's run analysis. And now let's check stresses in our system, and we see that everything is very good. Everything is okay. The sustained stress is very low. It's much lower than allowable stress. It is just the stress ratio is just 2%. So the same with the expansion stress. Expansion stress is 0 and allowable stress is very high. So we don't have any problem with this model. So we can think that this design is okay. But now let's open the project settings and select add the axial force and torsional stress. Now run analysis again, and now we see that we have the problem. Open the stress table, and now you can see this is the stress table without axial force, and this is including the axial force, and we can see that stresses, the actual stresses, are very high. So let's check the value of the stress. You can see that it is calculated like axial force divided by the pipe cross-section area, and it is used in this equation, and the final result is very high stress. It's much greater than allowable, and here is the allowable stress. Here is the allowable stress. This is number of cycles, the F factor, hot allowable, cold allowable, and this is the final allowable stress. And our stress calculated with additional stress from axial force is greater than allowable stress. But if we will use the original code stress, it will be 0 because there is no axial force. Another issue is in ASME B31 free code. To explain this problem, we need firstly check the expansion range calculation in another code, in ASME B31 code. Here is that equation. This is expansion range stress that equal to the bending moment divided by section modulus and multiplied by the stress intensification factor. The section modulus calculated using this equation that depends on the effective branch wall thickness. And effective branch wall thickness is the minimum value of the wall thickness of the pipe matching to the header, and wall thickness of the pipe matching to the branch multiplied by stress intensification factors. Where did this equation come from? The explanation is very simple. It is very simple. We need to check 2 points of the T connection The first point is the intersection point between the branch and the header, and the second point is on the branch. Here is the second point, this is point 2, and this is point 1. So here we have the stress intensification factor, and we use the wall thickness of the pipe matching header. And in this equation we use the wall thickness of the pipe matching branch, and we don't use the stress intensification factor. We can convert this equation to the simpler using the effective wall thickness, that is minimum value from TH and I multiplied by TB. The same idea is used for sustained stress, but here they use another value. It's 0.75 multiplied by stress intensification factor. And in this case, this equation is simplified to the following equations, and everything is correct here. The effective wall thickness is calculated using the 0.75 multiplied by stress intensification factor. Everything is correct in ASME B31 code. But now let's check the ASME B31 code. If we will follow the same logic, we need to check stresses in 2 points. The first point on the branch, and the second point is intersection point between 2 pipes. Here we should use the stress intensification factors, and as this is the sustained stresses, the stress intensification factors should be multiplied by 0.75. And for the branch, we should not multiply the bending moments by the stress intensification factors. Here we use the TB, and here we use the TH. But let's check the original code equations. It is following, and now if we will substitute the effective wall thickness intersection modulus and then substitute section modulus in the bending stress calculation, bending stress equation, we will get this formula. Now let's compare the correct equation with the equation that we get. Now we can see that stresses in the intersection point between pipe and between header and branch are correct. This value and this value is equal. It is correct. But if we will check the second point on the branch, we will see that the code stresses are 25% lower when it should be. So if the outplane bending moment is 0, you can see that we underestimated the stresses by 25%. If we will assume that in plane bending moment is 0, and let's take the outplane stress intensification factor equal to 1.4, we will underestimate the bending stress by 20%. How to correct this? We can substitute the correct bending stress formula into the equation and replace the original code equation by this correct equation, where we calculate the stresses in 2 points, in branch and in the intersection point. And also we should use the accurate value of header section modulus and branch section modulus. But unfortunately these corrections can be made in the software because ASME B31 free code revision needed. So we can only recommend to use the ASME B31J code that contain more accurate stress intensification factor values. It is very easy. You need just to select this option in PathStarProf project settings, and after that StarProf will automatically take into account the stress intensification factors according to ASME B31J, and also it will use the accurate real section models for header and for branch. And also StarProf will automatically convert all the T's in your model to the more accurate model with the rigid element with length equal to the half of diameter of header, and automatically it will add the flexibilities on the branch and flexibilities on the header. So StarProf has 2-layer model. The first layer is the model that you can see, that the software user can see, like this. But after you push the button Run Analysis, StarProf will automatically convert the original T's into the complex T model that takes into account the flexibilities of the header, the flexibility of the branch. It will automatically add the rigid element, and also StarProf automatically will take into account the greater thickness of the header and greater thickness of the branch if you will specify the T height and T length. It will be done automatically. But even if you will not select this option, if you will not select the ASME B31J, StarProf will continue modeling the T's using the rigid element, because it is important to exclude the unnecessary flexibility of the branch from the model. So StarProf will always use the rigid element here, and the model will become more rigid than if we model it with using just connection between 2 pipes, the header pipe and branch pipe. So this model is more correct with rigid element. Thank you for your attention. See you on next seminar. Thank you.